welcome back to the Colloquium of today. So we have, it's a great honor for us to have as our speaker Michael Rich from UCLA, coming all the way the long distance here and managing to overcome the jet lag. And so Michael Rich did his PhD in Caltech in 1986, and then went to Carnegie from 1986 to 88, Carnegie Fellow, and then at Columbia University in 1989 became an assistant professor. And then he moved back to Columbia. Moved to Columbia University as a senior research scientist from 96 to 98, and then from 98 onward became a research professor at UCLA. And so we're very happy to have him, and he will talk today on composition and kinematics of our Bulge. And so let's give him a warm up.
Those are adjusting the news. Well, thank you very much. It's a pleasure to be here. It's been wonderful to be in Heidelberg. I've been hosted by Andreas Koch, and we've had a marvelous time exploring the city and trying to do a little bit of work here and there. So today I'm going to talk about a number of, there's a lot of people, including Andreas, who have really been critical in contributing to the various research programs, really many different projects that I'll be talking about today. And without these valuable, energetic collaborators, nothing could really happen. So the reason we're interested in Bulge is that it's actually an interesting opportunity. We have, there's spheroidal populations. Ours is 100 times closer than M31. And they come, it seems now, in kind of two flavors, either true spheroids or something what we call bars. They're often called pseudo-bulges, but really I would call them bars or secularly evolved disks. So the canonical picture, if you look at a dark matter simulation, I'm sure you've all seen how the dark matter halos crash in and build bigger things out of little things as a function of redshift. That's the way we think that spheroids form. Secularly evolved galaxies don't seem to make their bars that way, which is interesting. So we're very fortunate to be able to study in detail this interesting stellar system that isn't formed the way we think that most of the systems are formed from this LCDM scenario. So any stellar population can be described by age, structure, kinematics, and composition. Those four kind of major things. I guess one could also say, of course, as Grabel's work so beautifully shows, that there is the star formation history and enrichment history, which we'll also consider. Although in the case of the Bulge, at least in my view, that's almost instantaneous and maybe hard to resolve. Now, these show a couple of different scenarios of how our Bulge may form. Body et al. Is the more traditional Engelin and Bell and Sandage translated into LCDM. And the left here is the idea, which is in fashion again, of clumps which might produce, say, spikes in the distribution of magnesium to iron. In fact, I think this scenario, at least of different chemical evolution environments merging into our Bulge, I'll show today, is probably not sustained by the data. This is the early work of Norman et al. Rahan Selwood in '91, I think. It's one of the first publications of this idea of a massive disk forming a bar and dynamically forming an M=2 disturbance and then making a bar. And then here's actually a bar, Combs's bar resurrection scenario, which is interesting, but I'm not so sure that I think we will actually see that in nature. But there are certainly many n-body models, including the one I'll show later, that form bars. Just so that people who are maybe not familiar with what we're talking about, this is the classical spheroids. This is NGC 7814, and we have a strong central spheroidal component, maybe a weaker disk, but there is a disk. And then NGC 4565 maybe looks a bit like the Milky Way would look like, as I'll show in a moment. Actually, our Milky Way, if you see an X-shaped structure here, actually these are real, and the Milky Way appears to have one of these, an X-shaped bulge. We call this boxy because if you look, this is kind of a little flattened. It's almost sometimes called a peanut shape. So these are these two. And then if we look at these face-on, there's the Milky Way here with a bar in Robert Hertz's beautiful diagram. M31 maybe at low surface brightness levels has a bit of a box structure. Here's, of course, a very strong bar. And then M81, which is a classical bulge seen face-on. So that way, you know what we're talking about, and you see where the Milky Way fits in to this scheme. There are some influential ways of thinking about these early papers. Cormier and Illingworth, 1982, where the idea of cylindrical rotation, pattern rotation, was first seen in certain classes of bulges, especially NGC 4565. And then the kinematic distinction that boxy and peanut-shaped bulges are probably edge-on bars was in the later Bureau and Freeman paper. Here's some beautiful images here. There are a lot of these boxy bulges. I think there's a recent paper that says they're quite common. And you can see there's kind of a distinctive thing of rapid gas rotation and then kind of a filling in of the LV plane. This is what we're looking here is the image, and then placing a slit across here, we have position and velocity from minus 500 to plus 500 kilometers per second. So these things are rotating rapidly, and you can see a particularly dramatic one here. There's a lot of complex structure, NGC 5746, and all of these have these peanut-shaped bulge structures in very similar kinematic profiles. So what you're looking at here is the velocity of the gas as a function of position, and there's bimodal velocities here. Actually, we see this kind of thing in the Milky Way in CO and also in neutral hydrogen, and you can see this kind of analogy a bit with NGC 5746. I would always look at this CO and say, I don't understand what is going on here, but if I look at this, I get some idea of what is going on here. I feel that there's this analogy, and indeed we have an edge-on bar. Recently, Beck and Gerhardt have analyzed a beautiful survey, the VVV survey, which covered roughly a couple hundred square degrees and continues on. It's a variables in the Via Lactea. It's an infrared survey in the YJHK bands with repeat cadences. These are trivial stars. And what Beck and Gerhardt did was de-redden the data and then look at the distribution. What you have here is latitude in degrees from +5 to -5. That's along the plane, and then depth and magnitude. So what you should picture here is looking at cuts through here. So this would be galactic latitude. And then they're spatially studying this structure. And actually, it was first discovered by McWilliam and Zoccoli in 2010 that there is an X-shaped structure. And then with later studies, Saito et al., we could see these actual kind of clumps in space. So it's like an X in space, and you're slicing through it. You're taking slices through this in different, see, each one of these boxes represents a different galactic latitude. So it's like you're slicing this piece of this sausage on the side. So then, Megan Gerhardt did a beautiful reconstruction of what we're seeing. And you can see this is actually a real reconstruction. This is what we observed. It was well known since Blitz and Spergel in 1991 that the plus latitude side of the bulge was thicker, and that led to their model of a bar roughly pointed 20 degrees. Now we have the angle here is now constrained by the Megan-Gerhardt model to be 27.3 degrees. So here we're looking at the bulge from above or in plan, as we say architecturally, and here we are looking at it in elevation. And as Orthan likes to say, this is the dinosaur's view of the bulge, because 60 million years ago, the Earth would have seen the X-shaped structure easily face on. But it waited for us until we had more intelligent brains to have to deconvolve it. So, but this is really kind of a major discovery about the structure of the galaxy. Now, I could end my talk right here, as I like to joke that when I took my kids out to see Gravity, I said if this movie was actually, up to the standard of physics, everybody would have been killed in the first 30 seconds. They would have rolled the credits, and then we could all go see the action movies that they wanted to see. But actually, there's a lot more to talk about than just the structure of the bulge. Yes, it's a bar. This is what the bulge looks like on the sky. This is the two-mass image. Now we kind of blow this up, and here is the bulge, Bottom's window. This is where the Sagittarius dwarf is in space, roughly. There's the northern bulge, where we would like to continue our Blanco-Buchan bulge survey that we'll talk about later. So this, to give you a sense of scale here, from here to here is about 500 parsecs, and the galactic center is about there. One of the great advances in the bulge came with this landmark paper by Clarkson et al. 2008. They used the technique of proper motion cleaning to actually isolate from the color magnitude diagram. Overall, you can't, you would see a strong main sequence of disk stars which lie in between us and the bulge. But by vetoing stars with large negative L proper motions, they were able to remove those stars based on kinematics. And this color magnitude diagram suggests that the vast majority of stars are around 10 years old, or 11 years old, it's hard to say. And then most of these, it turns out, are actual old blue stragglers, not foreground or not in situ young stars, based on there being SX Phoenicis variable stars. That is, a number of these are variable, and kinematics and colors and so on confirm that these are genuine blue stragglers in the bulb. However, this assessment of age is disputed because this group, and Thomas Bensby has probably been through here at some point, what they have done is taken advantage of the fact that bulge dwarfs can be microlensed by an even lower mass star that passes in between the sun and the star of interest. When the alignment is good, you can get amplifications of up to 1,000. And in fact, there is even a proposal for the W1st mission of NASA to search for planetary spikes in these extreme microlensed events, which in fact can be quite interesting. And they have actually gotten down to Mars-sized planetary constraints. That's another topic. But one of the things that can be done during the peak amplification period, which is a few hours, is to take a UVES or high-res spectrum of the dwarf. And this has resulted in a beautiful abundance distribution function here, which unfortunately the authors have elected to deconvolve into multiple peaks, which I do not agree with. There is one distribution function and it fits the simple model of chemical evolution, as I showed in 1990, and that's it. I don't believe there are multiple peaks. That issue is still debated, but anyway, they assert that there are multiple peaks. But more significantly, when you solve these spectra self-consistently for gravity and effective temperature and place the stars in the physical HR diagram, then you can get ages, effective ages from photometric or spectroscopic ages from the self-consistent stellar parameter solution. And this group asserts that roughly a quarter of the stars in the bulge, maybe as much as a third to a half above Fe over H minus 0.5 or so, are young. The problem is that we should see such a population in the color magnitude diagram, and at the moment, I would say that there is no evidence for that population. I think that the HST Treasury project ongoing, Tom Brown PI, is exploring the issue of the age of the bulge for various constraints, and I think they are also not finding evidence for that population. Turning to kinematics, the Bravo project, actually I couldn't believe it, but it had its 10th anniversary last year in 2013, but the first proposal was in 2003. It took some time to get it actually approved. The idea was to use M-giants, which are bright stars, and to use the CTIO 4-meter plus Hydra to measure radial velocities for M-giants over a large fraction of the bulge using the TIO and calcium infrared triplet region. This shows the schematic being filled in the colored field, showing where we actually were able to get data. So we did a rather dense grid from -4, actually there were a few fields at -2, all the way out to -8. This has been extended inward by the Gibbs survey horizontally and extended outward by the Argos survey of NEXT. Here is our target selection. You see, we wanted to stay within a magnitude of the red giant branch. We didn't want to get too bright for fear of picking up disk and foreground stars. So we used a D-rating selection box, and then we extended the selection a little fainter when we went to the -8 or 2 kiloparsec field where there was fewer targets. We initially thought that we, in looking at the line of sight velocity distributions, had found a number of streams, but every time we added data to one of these streams, they went away. And so we're now chasing down one stream, which Andrea Kunder is working on, and which I am going to let her tell you about at some point. But I'm going to leave that to Andrea to tell you about it. It is potentially quite interesting. Then we, using the Brava data, we constructed an LV plot, longitude radial velocity, -400 to +400. This shows -4 and -8. And you can see here that the rotation field has the same slope. So this is the cylindrical rotation. These plots here are from Zhao's 1996 self-consistent model. We have recently updated this with Wang's model, which I neglected to put in, but the fits are actually very beautiful. I should have put in, but there are so many things happening. And then this shows -4, -6, -8, and you can see as you go, as you decrease in longitude, in latitude, the velocity dispersion decreases. You can see here's the run of velocity dispersion as a function of galactic latitude. And you can see there are some outlier stars. There are interesting things to note about these LV diagrams. And one is that were there a cold population of stars that had infallen from a dissolved dwarf spheroidal or something like that, or a more massive object, there would be a kind of a line through here where the stars have been distributed, assuming it was a massive enough system to populate the LV space. If there were a substantial, hot, slowly rotating spheroidal component, we would see stars filling in over here. Cormandy was very excited for us to look at the corners +8, -8. He thought that we would find a classical spheroidal population. We didn't. But there are a few outlier stars, and you can see that there are some potentially interesting things that are in fact being followed up. We compare the Brava survey with Bulge et al.'s planetary nebulae survey. This was a pathfinder project. It was very imaginative. Planetary nebulae are bright. It's easy to get their velocities from the oxygen 5007 line. I suspect that some of these low velocity dispersion measurements here in the planetary nebulae reflect that they're either being, the distances being uncertain and they're being closer, or they're being members of the disk. This shows an overlay of all of our data. This is from Kunder et al. 2010, with a fit of the Shen model that I'll talk to you about shortly. And here you can see very clearly the cylindrical rotation. That is, the rotation field doesn't really change as you move away from the galactic plane, whereas in a classical bulge, it does rotate more slowly away from the plane. This is the velocity dispersion profile. And here you can see, more very nice fits. The velocity dispersion profile as a function of latitude. And now this shows the comparison of Brava and Argos, which is the Ness and Freeman survey. So Argos is less densely sampled, but spans a wider range in galactic longitude. And here is the Ness data, and they confirm the cylindrical rotation. Something that is interesting that they find is that the most metal poor part of their sample appears to have slightly slower rotation than the most metal rich part of their sample. You can see, especially, this is -20 to +20. So this is twice as wide as Brava, and the metal poor stars selected from these fields are indeed more slowly rotating. And also show different velocity dispersion profiles. The only problem is that it's not clear whether these really are members of the bulge. Remember, those are 2 kiloparsecs away from the galactic center, or whether they're looking at possibly members of the metal weak thick disk. The contamination from the thick disk at these greater distances is going to be substantial. Another recent claim that has appeared in literature has been by Heidelberg et al. From Apogee, and there's been this 200 kilometer per second peak that has been seen in their initial data. This would be very exciting because it spans, if you look at these numbers here, this is L and B, and we're talking about this peak being basically everywhere in the bulge over the inner, say, 2 kiloparsecs. It would be a huge feature, potentially some kind of cold stream or ring structure, not clear what it would be. It certainly doesn't seem to be reproduced in any bar model. This is Shen's bar model here, and the red features, the red arrow shows where the peak is, and the gray are the models, and there just isn't any way to get that peak. And this is, by way of example, a survey at the position of Terzen 5, which is near one of these peak features, and this was 1,600 stars with Deimos at Keck, and there's no detection of the feature, and Gibbs didn't find it either. So we think that there is, a problem with that claim for the plus 200 kilometer per second feature. It's something that is going to have to be followed up, and I think that the Aberdeen team now has substantially more data. Now let's see if this works. Well, half the time I can get this to work, half the time it doesn't. And unfortunately, I think that we are...
Maybe you can go off the presentation and then...
No, I think, yeah, it's been dangerous to, I don't know what that means. It may be the version of, but, okay, what it should do is it's a pity because it is nice and it does work, but it doesn't seem to be behaving. But it will turn into a nice peanut-shaped bulge and oscillate. And actually, this thin disc kind of forms the bar, and then you see the vertical oscillation as it forms the peanut-shaped bulge that you can see here. This is actually an N-body model with 1 million particles done by Jindai Shen. This also actually makes a X-shaped bulge, though not as prominently as the Wegener-Gerhardt model, but it does produce a pretty prominent X-shaped bulge. And what we were able to do in Shen et al. 2010 was to fit the Brava data in these models. It's a beautiful fit. And from this, especially from the minor axis profile, you can get a constraint on the fraction of the bulge that could be in a classical slowly rotating bulge, rather the fraction of the total disk mass, which is really in the simulation largely mapped into the bulge. It's about 10% that could be in a classical slowly rotating bulge. Now, there are a lot of gotchas here. There is a paper by Saha and Gerhardt where they point out that if you have a rapidly rotating bar that forms later in a classical bulge, it can spin the classical bulge up. And so it could be indistinguishable, and you might have a substantial mass of stars in the classical bulge. I think that, one of the things that is emerging both from the work of Ness and the Gaia ESO survey is that the majority of stars that are in the X structure and are strongly barred are metal-rich. This also is something, by the way, seen in the Soto et al. Papers, which I didn't include, but there are 2 papers from 2007 and 2013 which use the technique of vertex deviation to show that the majority of metal-rich stars are in fact participating in the bar. So when you take that into account, I think the idea of the classical bulge being spun up is less attractive. So basically, the conclusions from the Brava survey, the really important, significant conclusion is that in principle, the bulge did not require a spheroid at all. The bar could have evolved from a pure disk, and so as Cormany refers to the Milky Way as a pure disk galaxy, and that he feels is significant. Of course, how does something like that survive over time in an LCDM universe? And the other thing to take away is that Brava was the first survey to get a stellar rotation curve and also to discover cylindrical rotation and to fit with various bar models, both n-body and self-consistent. There is an interesting problem. There is definitely an abundance gradient in the bulge. It's been known for many different methods of measurement. This was high-resolution work from Zachary et al. 2008. It was also discovered in the infrared, asserted in colors, in optical colors, and it's well established outward of -4 degrees. Inward of -4 degrees, there's too much extinction to do really good abundance measurements, but an interesting thing is seen. And that is that the abundance distribution is both surprisingly narrow, slightly metal poor, and there is no measurable gradient. And in fact, the lack of really metal-rich stars is now extended into the center by the recent work of Reed et al., which produces an abundance distribution in the galactic center region similar to this, for a sample of 9 stars. We're beginning on Keck with a program that will hopefully get 100 red giants with the near-spec spectrograph within 50 parsecs of the galactic center that are members of the central cluster, and we're hoping to understand this abundance distribution better in the galactic center. But within the 4 degrees, where, interestingly, by the way, the X-shaped structure is not detectably prominent, one does not see a gradient. There are n-body models that try to begin with a disk that has an existing abundance gradient. This is a nice piece of work by Martinez, Valpuesta, and Gerhardt, which seems to produce rather well what is observed in the bulge. And it's roughly right in terms of the magnitude of the gradient. Where there isn't a gradient and where there is, the model begins with a disk that has a radial abundance gradient, and you get this interesting result. I personally, however, believe that the gradient may be related to either one of two things. The fact that the bar is very metal rich, and maybe there is some other component that's metal poor, maybe the inner halo. The other possibility, which I've always liked, is the idea that there were that metal entrained winds early in the formation of the bulge. You can see winds in the case of M82, and all the winds have to do is remove metals from that region where the intense starburst is occurring, and maybe remove them a few kiloparsecs away into the disk. Then the Brava survey also plots the Milky Way bulge on the Bidding diagram, which is maybe a less useful construct than it was when it first came out, but it places Milky Way near NGC 4565, and being that both of these are peanut-shaped bulges and probably edge-on bars, it's falling on the oblate rotator Bidding line, and so it is consistent. Indeed, however, what's interesting is that there are these abundance gradients. This measurements by Proctor et al. Clearly found both iron and magnesium abundance gradients in the bulge of NGC 4565. And in addition, you can see the kinematics. This goes back to Coleman and Yelling of 82. So, in fact, abundance gradients are probably ubiquitous in these boxy peanut bulges. So this goes, now we go back to this thing, okay, if the bulge is a boxy peanut structure, how is it that it's old? Because secularly formed structures take time to form, and in most of the models, it can be substantial, some gigayears to form. This remains a problem, though I think the models will figure out how to form secular structures quickly. By the way, the Brava data set is a public data set. In fact, Gerhard has recently used it. He presented some very nice work on the dynamics of the bulge, where they fit the Brava data set extraordinarily beautifully. We made public the spectra every basically all the data that we have. So that does the problem. Now we turn to the abundances. We selected, this is in collaboration with Christian Johnson, we selected stars from the red giant branch and also a set of red clump stars in the foreground. This is in the -8 degree field. And what's interesting, and something that we need to get back to actually, is that the red clump stars in the foreground show the same alpha enhancements as the bulge stars. And in fact, alpha Fe, with all of the alpha elements, is found to be enhanced uniformly all over the bulge. And this is true even from the infrared spectroscopy for stars within a degree of the nucleus. So this is a signature, and as we know, the enhancement of alpha elements is supposed to reflect the rapid enrichment of the bulge due to type 2 supernovae that produce the alpha elements in hydrostatic burning. Another interesting thing about the bulge is its heavy elements, and this is something that one area that I'm really enthused about. This plot of lanthanum to europium is interesting because lanthanum is predominantly an S-process element that would be produced by intermediate mass AGB stars, europium an R-process element associated with supernovae, though now a number of people believe the R-process is due to emerging neutron stars. Lanthanum to europium shows this ratio shows that the bulge falls closer to the pure R-process line, both two bulge studies, and the disk is up here, and then there's one pure S-process star here, which we got a spectrum of last week, and then there's one very europium-enriched star there. Here's europium and iron following an alpha-like trend, and then here you can see the little small black points here are the thick disk and the red points are the bulge. And although we need larger samples, I think it would be fair to say that the bulge has more R-process-like excursions than the disk. So we focused on this star here. It's got Fe over H of -1.7 and europium to iron at +0.93, which is really high, especially at this iron balance. There's only one other star known similar to it, and it's COS 82 in the Ursa Minor dwarf spheroidal galaxy. Now, we analyze a number of elements here, and this is a complicated plot, but the takeaway from this plot is normalizing to europium. This star looks like the most classical R-process super-enriched stars like CS22, -52, the classic ones like COS 82, which is also R-process enriched. But bear in mind, this is in the bulge, and it is sitting at -1.7 dex. Most of the stars that are whopping europium-enhanced, R-process enhanced stars are found down here at -3. So we'd like to know if there are a lot more stars in the bulge like this, because this might be giving us a little insight into the very first era of the bulge's starburst, which may actually have occurred well after the halo initial enrichment period, because when the latest work of Hawes et al. Finds a number of stars at Fe over H -3 in the bulge, these stars are not necessarily of the bulge. The distinctions between the bulge and other populations, though, are somewhat subtle. I mean, for example, if you plot sodium to aluminum versus iron to hydrogen, you can see that there is a different slope here, and this is confirmed in more recent work. Sodium to iron versus iron to hydrogen has a different slope from these other stellar populations. Sodium is maybe what we call secondary element, so we're looking at a situation of perhaps a metal-dependent yield. but the interpretation of this, there are no models that fit this. We have done a recent study of archival VLT data in two bulge fields, one at, off of the minor axis at +5, -3, centered on a globular cluster, the other one on the minor axis at 0, -12, about 1.5 kiloparsecs distant from the nucleus. And here you can see the loci of the stars relative to the red giant branch in these two fields. The earlier work found this level of scatter for iron and hydrogen. The work done by Johnson et al. Finds this level of scatter, 5 decks. But it was necessary to get this scatter to also reject a number of stars that had been measured by earlier. And the stars that were rejected, unfortunately, they were measured using an automated code called DAO spec. And this star in blue here is filled with titanium oxide absorption lines from a molecule. And an automated code will just sit on these lines and think they're iron and give you a very fancy iron abundance, which is wrong. And it'll also give you very interesting abundances for other elements, which are also wrong. And so Johnson went through and basically rejected the contaminated stars based on effective temperature and spectral appearance. Here's the velocity distribution, and then this is a plot here of velocity dispersion versus iron and hydrogen, which now we find in all bulge fields shows a very strong tendency to have a steep dependence from -1 dex to 0.4 dex, and this is a really steep change in velocity dispersion. This is a problem if we're talking about one dynamical unit. There are a lot of contradictions, and observers really need to remember these contradictions as they study this problem. And this velocity dispersion decline as a function of metallicity is not really consistent with the idea that, well, we have this bar, and all the metal-rich stuff is in the bar, and that's that. So there is a lot of work to do in really understanding what's going on here. This just shows the new abundance distributions relative to old ones. We do better at getting the metal-rich stars. We fail to see any multimodality that is statistically significant in the abundance distribution. Here are Johnson et al.'s beautiful abundance trends. If I may say so, but this is really amazing. This is oxygen to iron as a function of iron to hydrogen. And this is calcium, chromium, cobalt, nickel, and copper, which is quite interesting, metallicity dependent yield likely. Silicon, there are subtle differences. Silicon, aluminum, now it seems to have an alpha-like trend for the first time. Magnesium, which is actually not as enhanced as solar as McWilliam and Rich initially asserted. And sodium, which now we do not find the large population of stars above 1 dex that Lake Ruhr found. And here are some trends of oxygen and magnesium versus iron and hydrogen. And very interesting, this trend here suggests that the copper has a massive star origin, but it may have multiple origins because at the metal-rich end, you would start to think that copper would be predominantly originating in type 1a supernovae. But we really don't know. This is a very strong abundance trend of copper-iron versus iron and hydrogen. We can't say for sure, what the origin of this trend is. I won't even show you the fits of chemical evolution models because they don't really constrain much. Because we're lacking the metal core stars where they have strong constraint. Now, what you see here is our work compared to literature work on the giants and the dwarfs, particularly by the very beautiful work of the Bensby et al. Group. And you can see that the abundance trends are very clear, they're reproduced, and that regardless of where you're working in the bulge, all over the bulge, these trends appear to be the same. And in addition, you'll notice that there are virtually no stars down here, or here, or here. And that's where the dwarf spheroidals would live, but there are no stars in the bulge that look like dwarf spheroidal stars. So one of the important conclusions of Johnson et al. Is that we have very little to no contamination or, say, contribution in the bulge by dwarf spheroidals that have dissolved. Now we can compare the bulge to various other Milky Way populations, the red stars in the bulge, thick disk, thin disk, and we can see that in oxygen they are the bulge is quite dramatically different, less so than one would have expected in magnesium. Silicon, bulge is high, and calcium, there is some scatter. So this plot even surprised me a little bit. I remember originally with William and Rich, we were wowed by the magnesium and titanium abundances that were high. It's a more subtle effect. The thick disk has a lot of bulge-like feeling to it, which in fact, you might expect if the bulge originated from the disk. Here are this particular trend is quite interesting. Sodium to iron, that now with our new sample, very high quality data, we see, this strong trend of sodium to iron versus iron to hydrogen, which may reflect the metallicity-dependent yield. But this is something where the bulge is really different from the disk. And this may be a way, by the way, to isolate, what we call first or near first generation bulge stars, which I think is a very important thing to do in the next few years. And then this is iron. This is aluminum to iron versus iron hydrogen, and the trend here is very much alpha-like, which is also a unique result for aluminum. So these are the conclusions from Johnson et al. That the bulge alpha trends. I don't really need to read these. The copper. The one thing that's interesting, by the way, is the Kobayashi models may favor hypernovae. I think we just don't have, unfortunately, the data that we have are not as constraining of chemical evolution models, and maybe the chemical evolution models need more detail in them, but in any case, we were not able to get really strong constraints from fitting chemical evolution models, except that we don't need a really anomalous IMF. And I guess I'll mention briefly that there's a lot of work still to do on the abundance gradient. It's really a lot of work, actually, so I'll skip over that. One interesting object that you may have heard about is the globular cluster Terzit 5. It's a massive cluster. It was first discovered to be remarkable with this use of the multi-conjugate adaptive optics demonstrator at the VLT. There's a double red clump that was discovered by Ferraro et al. In 2009. Then we went and got spectra of Keck of stars in these two clumps and found that there was quite an abundance spread. We went and got more spectra and found that there was a really crazy abundance spread. The solid filled symbols are members of Terzit 5 with identical kinematics. And yet, if you look here at FE over H, separated by 0.5 dex in FE over H, the other symbols are globular clusters in the bulge and field stars in the bulge. Notice that, by the way, the metal poorer population is enhanced and alpha is just like the metal rich. We're working through HST and adaptive optics data to try to get a constraint on the ages of these two populations. Because if you look back here, an interpretation of these two red clumps is that there might be a 6 gigayear age difference with the metal-rich population being 6 gigayears younger. The most recent abundance distributions from the near-spec work and also from a larger scale survey with Deimos find that there's even a peak at minus 0.8 Dex. So this is within one stellar system having a, and possibly even this star is a member and real, and there may be 2 or 3 stars in that peak. So we're talking about a system that has somehow been able to retain its gas and experience multiple bursts of star formation, yet looks like a globular cluster. It's been suggested that this is a survivor of a once massive population of galactic nuclei of the systems that originally populated the bulge, a la the Emily plot I showed earlier on in the talk. But the problem is that, you know, we don't see any other clusters for the moment, and we've been looking at a number of massive clusters in the bulge with an abundance spread like this. There are a couple of clusters known with double horizontal branches, but they're not turning out to have a dramatic abundance spread. But this is going to become a very rich area because we've actually used the OSIRIS imager and spectrograph to get kinematics of Terzen 5. We're searching for a central black hole, but out of respect to the people who've done the hard work for that, I have to tell you to watch this space and search for articles on Terzen 5. I really can't tell you about that, but it is interesting. And so you'll hear about that soon, I think. Then the Blanco DCAM Bulge survey is a large survey that we're undertaking, which will ultimately roughly cover the VVV field of regard, with a special little attention to the Sagittarius Boreas galaxy. The dark energy camera is on the prime focus of the 4-meter telescope. It has a 3 square degree field of view. This shows our field on the sky. So it's one of the, I think it's now the largest imaging camera until LSST comes online. This is the focal plane here, a view of the chips. And this is part of an image. So it makes very, very nice images. We're getting subarc second images in many fields. This shows you can read out some of the focal plane. Remember, there are 62 CCDs, but this is cool. This is the readout room at Cerro Toloa. You can kind of get lost in space. And then Will took this focal plane here. This is Bada's window to globular clusters. This shows where Bada's window fits in our mosaic. And this is a diagram that shows how we overlay various space-based imaging fields, including GALAX, X-ray surveys, and so forth. We have, we're covering everything contiguously. We've now finished this whole square, save this little piece here, which we hope to get next year. We hope to get this completely filled in and start working our way toward the north. Here is a color magnitude diagram, preliminary. Here's the main sequence turnoff, the red clump. This is possibly where we see blue HP stars. We have U, G, R, I, Z, and Y. So in contrast to VVV, we extend all the way to the U, where we really hope to see the faint blue horizontal branch. The data are now standing at 5 terabytes. They had to be reprocessed because on the initial run, the World Coordinate System failed for 15% of the 62 CCD images, and it's an irretrievable problem, but luckily they improved the community pipeline. So there's a community pipeline that gets you to the point of ready for photometry, that is bias attracted, flat fielded, etc. Then we run DUPHOTE in dual pass. This is done by Christian Johnson and Scott Michael, who used the Corey supercomputer at the Indiana University Pervasive Technology Institute. And so we're just at the moment in the process of reducing all the data. And then Rade Bada is going to do a parallel reduction on an Apple computer that we hope will not be set on fire by the attempt to reduce all that data. So we hope that perhaps in a year or so there will be some very interesting things. Our science goals with this are to map the structure of the bar as a function of metallicity. There are indications from Kane et al. That our Lyran population does not participate in the bar, that there is a substantial metal pore population that is not in the X shape, and we hope to be able to really see that vividly when you have V minus K, the power of the blue colors, to derive very detailed abundances, or not detailed, but at least get at the 0.3 depth level for individual stars is pretty good as opposed to what you could do in the infrared. So we are then looking forward, we hope to get second epoch proper motion data in 5 to 10 years, or just use the LSST, and then we can proper motion clean the entire area, a few kiloparsecs, 400 square degrees, and actually see the locus of the bulge as a function of age and metallicity over these broad scales. Thank you very much.
So, thank you very much for this nice talk. I would like to open with the questions from the students and postdocs. I'll also make a little bit more light. Any questions?
Good one, when you said it at the beginning, I can remember a bit. So how do you assign stars, especially based on color magnitude diagrams or multi-band colors, how do you assign those to a bar, to the X-shaped or peanut bulge, to the, if there is one classic bulge, to the disk, to the thick disk? How do you use your just?
Oh, yeah, this is for the spectroscopic subsamples, or
I don't know.
oh, for the Wegener-Gerhardt.
In your spectroscopic, you probably know the intrinsic luminosity of the
The
star.
Wegener-Gerhardt study, which I think you're maybe asking about, the one that reconstructed the peanut-shaped bulge. What they did was they looked at the red clump, they deremmed the VDV data, and they focused on the red clump. And since we know the rough luminosities of red clump giants, we're able to actually, you could actually build, and it's such a gross feature, it's like a 0.75 magnitude difference between the two X's, that you can reconstruct the spatial distribution of red clump stars only. I should think that in not too long they may be able to proper motion clean their data and actually do an even more detailed reconstruction using the red clump stars. For the spectroscopic stars, when you take spectroscopic samples from the RGB, there is something like a 10 to 15% potential thick disk contamination that one cannot avoid without a proper motion pre-selection that we do not have.
Okay, further questions?
You mentioned stars in the bulge which have strong enrichment in Europium, but are very metal poor.
Yeah.
How can you get such stars?
Oh, well, it's been long known that in the halo there is a subset of our process enhanced stars. I can quickly find the plot, which includes the halo. I can show this to you. This has been known actually since the work of McWilliam, Preston, and Beers. I think that's past it. Here. So all of these stars here, including CS2282-52, which is the star in purple, which is like the monster European enhanced star, the monster R process enhanced star. See, these stars here, they have the extremes of European iron go even higher. It's believed that early on in the halo, individual supernova or, as it were, neutron star merger events could have contaminated gas from which these objects form. So they're very interested in that region. There are also stars that are known with super enhanced alpha elements, lacking in neutron capture elements, some stars completely lack neutron capture elements. This goes the other way too.
Okay, let's open for everybody.
I have two questions. One is about the contamination by dissolved Doppler clusters. Do you see any oxygen-sodium anticoagulation at the moment?
No, it's, I think, something that we want to look at actually, I took a slide out that even within Terzen 5, we tried to look for aluminum-oxygen anticorrelation and didn't find it. And there is one case now of a stream that almost certainly is a dissolved, very metal core globular cluster, a 92 globular cluster, but it's got a handful of members. So it looks like there's, this is, even though you would think that globular cluster dissolution contributed to much of the bulge, and that it's the Chernoff and Jogovsky, all the bulge shocking zone. No, it's something that we'll, obviously want to look at in a larger survey, but a preliminary indication is no.
And the second question is about the central star cluster. What
Yeah.
the whole of that, you see this very steep density profile in the galactic center. This cannot be part of the bulge, of the bar.
Yeah, it's not, and probably not. I mean, it's almost certainly a dynamically distinct system. It's been very dramatically illustrated, but it also does seem to be old. At least an underlying part of it appears to be old. Although more work needs to be done there. The original work was done by Feiger and myself and others in 2004, and we did see that there was a population at least older than 1 billion years, and a clear red clump all the way into the galactic center. But more, so the question is how that relates. It's not completely clear, but it's certainly worth. It has red giants. We can get their abundances, and we should, and then we'll learn more.
Okay, further questions? Yeah.
Could you talk at all, you talk about the bulge, you talk about the bar, you talk about the thick disk. Can you just talk about how specifically the bulge and the thick disk properties transition from one another? You hinted at the chemical abundance, but what about the structure, the age that you guys observe?
I think that, this is an area of, that really needs to be actively worked on in the central kiloparsec, because the thick disk probably interpenetrates. The problem with thick disk samples that we have that are offered today, in fact, there's a school of thought that there is no true thick disk, so I'll just say old disk or kinematically thick disk samples, is that there are local nearby stars that are classified as thick disk. The transition is that the thick disk shouldn't reach the high metallicities found in the bulge. Not really, it doesn't even get near solar abundance, but the age could be very similar, if not indistinguishable. The scale height is similar, in fact, but the structure, of course, is quite different. But the distinctions are subtle. The bulge, the members of the bulge/bar have higher oxygen abundances. They have this sodium trend that is not seen in any other stellar population.
So you think just follow the thick disk in further and do you think it'll connect, or?
Well, I think actually it's likely that within the inner 2 kiloparsecs, the bar will dominate. And I think once we do, one of the nice things about VDBS, and actually it's possible that people working on VDB will get to it first, is that we have the potential to get distances for millions of stars and distance constraints for millions of stars. And so elucidate the structures there and see where the boundaries of these populations are.
Is there a further, would you like to
We can do that later. what question, you talk about it all the time, so can you tell us a personal question, Noe? What is your, at least working, if not theoretical definition of the classical bulge? Properties that would...
A classical bulge would be a spheroidal structure. If we look at, say, Cormany and Illingworth with 1982, it would have would not exhibit cylindrical rotation. It would not be peanut-shaped, and it basically would be a spheroidal central structure that does not exhibit the complexity typical of the edge-on bar populations. And in face-on plain view does not have any triaxiality. And that would be my definition. And maybe, perhaps one might say that overall, divocular profile and more centrally concentrated, more nucleated than a bar. But I don't believe that there is something called a pseudo-bulge. There are bars and there are boxy bulges. There are X-shaped boxy bulges that are extremely bar-like and extremely consistent with this, secular evolution picture, dynamical evolution of the disk. But I think there's a pretty sharp distinction between the classical spheroids. It's more of like, you look at MA1, you look at NGC M104, these spheroids don't show any triaxiality. They're not flat. They're not structured.
Last question.
So this is somewhat related. So you don't believe in pseudo-bulges?
This is a personal, and I could get into some trouble.
Like M33, what is...
M33 is a disk.
Is a disk with no bulge?
Well, people have claimed the bulge, but really now. Okay, maybe, if you look real hard, I think there's a nucleus, and maybe a central concentration to the nucleus. It's been batted back and forth, it's reading it out, when you see the bulge, but certainly not a pseudo-bulge. And then NGC 4736, I would just call that a late starburst structure that will probably evolve, that will probably move in the secular direction. It's a massive disk that will probably become a bar at any time. There might be some pseudo-bulges out there, and I would say they're probably late starbursts, and if John Cormany were here, he wouldn't be my friend anymore. So I have to be careful. It's just a personal, that's what you call it.
Okay, so, well, it's going to be online, so maybe you can make sure you're not watching it.
Oh, make sure he's busy hunting for more birds. I'm sure he won't.
Okay, so let's thank him.
Thank you very much.